Welcome to the Explainer. Today we're going to pull off a pretty cool trick, measuring a wave of light. I know, it's invisible, it's ridiculously small, but with some clever physics, we can actually pinpoint one of its most basic properties, its wavelength. So let's dive in. I mean, it sounds impossible, doesn't it? It's not like you can just hold a ruler up to a beam of light, but it turns out that with the right setup and a bit of know-how, we can measure this invisible property with amazing precision. So how in the world do we actually do it? Okay, here's our roadmap. First, we'll lock down our goal. What is wavelength? Then we'll get into the principle of how light splits. After that, the formula that decodes the secret. Then we'll peek at the lab setup. And finally, we'll put it all together to calculate the answer. Right. First things first, what are we actually trying to achieve here? Before we can measure a light wave, we need to be crystal clear on what we're looking for. So here's our mission, plain and simple. We want to figure out the wavelength of light, and our tool to do that is the laser diffraction method. Pretty much every single step we take from here on out is just to find that one specific number. So how do we even start? Well, the whole thing hinges on a really cool physics concept called diffraction. Let's look at the piece of equipment that makes this whole thing possible. The absolute hero of our story is this little thing, a diffraction grating. You can kind of think of it like a bouncer at a club, but for light. It doesn't just let the light beam pass through, it actually organizes it and splits it up in a very, very specific way. And this is where the magic happens. When that laser beam hits the tiny lines on the grating, it bends and fans out, creating this pattern of separate bright spots. These spots are called maxima, and they're the whole key. The exact spacing between them holds all the secret information we need. Okay, a pattern of spots is cool and all, but how do we turn a visual pattern into an actual number? Well, the answer is just pure elegance, and it's all inside one single, powerful formula. Here it is. This is the equation that runs the whole show. Now, I know it might look a little complicated at first glance, but seriously, just think of it as a recipe. It just connects all the different pieces of our experiment. Let's break down what each of these symbols actually means. First up, we've got this symbol here, lambda, or lambda. That stands for the wavelength of the light. This is our target. This is the mystery we're trying to solve, the whole reason we're doing this. Next, you'll see this symbol, theta, or theta. That's the angle of diffraction. It's basically the angle between the bright spot smack in the center and any of the other spots off to the side. This is the one piece of data we're physically going to measure in the lab. It's crucial. And finally, we've got m and n. Now, these are the easy ones. They're values we already know. M is just a property of the grating we're using. It tells us how many tiny lines are carved into it per centimeter. And n is even simpler. It's just which bright spot we're looking at. The first one out from the center, the second one, and so on. So check this out. With just a little bit of basic algebra, we can shuffle that formula around to solve for lambda, the wavelength. And just like that, we have a clear path forward. If we can measure theta, and we already know m, and n, we can calculate the answer. It's that direct. Okay, enough theory. Let's get practical and see how this all comes together in a real experiment. How do we get that super important angle measurement? The lab setup is actually pretty straightforward. You just need three key things. You need your laser source, of course. You need that all-important diffraction grating, and then you need a laser spectrometer, which is just a fancy tool designed to measure the angles of light really, really accurately. Now, the whole procedure is really about being precise. You start by making sure everything is perfectly level and calibrated. Then you align the laser so you can find that central bright beam. Once the grating is in place, you'll see the pattern of spots, and then comes the main event. You carefully use the spectrometer to measure the angle for each of those outer spots. That gives you your theta value. All right, we've gone through the theory, we've walked through the experiment. Now for the best part, the payoff. Let's put it all together and get our answer. And really, this is the whole point of the lab work. All that careful setup, the leveling, the aligning, it all came down to getting that one critical piece of data, the angle, theta. Now that we have it, we can finally solve the puzzle. So, the angles you measured fit really nicely into a simple table. For each spot you looked at, the first order, the second order, you just plug in the angle you measured. A quick calculation from there gets you to the final value for the wavelength. You literally just take your measured angle theta, the order number n, and the grating spec, mem, and you pop them right back into that rearranged formula we looked at earlier. And there you have it. That's it. By taking a simple pattern of light and applying one elegant formula, you've successfully measured something that's totally invisible. You found the wavelength of light. Which, it leaves us with one final thought to ponder. If we can measure the wavelength of light with a method this clever, what other hidden secrets about our world are just sitting there, waiting to be discovered with the right experiment and the right formula?